Okay, so thank you very much for the previous introduction, and many thanks to the previous lecturers for their comprehensive and really amazing presentation that I'm a big fan of. And with no further ado, let's just jump right into this topic. So maybe I could start with a pretentious question for you. So have you ever wondered how to start your journey in industrial IoT? Well, I asked myself the same question about 2 years ago when IoT really started to mesmerize me. And during this presentation, I would like to share with you my experience with working around this topic and those challenges I had to face, and maybe as well to try to encourage all those of you who are asking themselves the same question to maybe start working with IoT. And for those who might join us right now, my name is Rafał Siwek, and I am currently a data engineer at PGS Software. So my journey in industrial IoT was not that obvious. So I graduated the technical university as a control engineer, and I did not start work in IT right away. So I got a fairly good job at one of the leading industrial sensor suppliers and had a chance to implement, maybe even work with IoT solutions in the enterprise level. So while doing that, I had a chance to implement a lot of several IoT infrastructure, but from the hardware level. And that became more and more interesting for me. To this point, I said, well, now it's time for me to rebrand myself and start gaining knowledge from the software sides. And that's when the change came, and I met my mentor at this current company. And from this time on, I had to gain a lot of knowledge, which was quite fairly new to me. So, well, while doing the research, I actually became overwhelmed with the amount of IoT platforms. Well, according to IoT analytics, I just wanted to put this quite boring statistics, but they mention one major point. So in last 5 years, the number of publicly known IoT platforms overly doubled at the market. And yeah, to this time, we might also have to deal with about 360 known IoT platforms offered by various providers. And some of them are quite popular in the industrial sector, like Siemens, Bosch, or Schneider Electric, and even others that, for example, for me, previously, they were never familiar with IoT topics to be familiar with it or related to that. So that meant that, yeah, IoT solutions, even in the industrial sector, are getting more and more interesting. And to stay competitive in this area, we might have to be familiar with all the taxonometry around that. But where to start with IoT mainly, with the common uses IoT? So for me, I started just to taking one of the more common sensors that I had to work previously and started to collect the temperature data and visualize it on a dashboard service, and all that was placed on a Raspberry Pi. Well, that looked something like that, and I was quite happy with my achievement. Though, let us agree, Raspberry Pi is not quite industrial friendly, and although this is no enterprise level solution. So by working with a lot of different cases, with a lot of different customer requirements, it became clear that although it is quite neat to have a real-time dashboard solution, but there are a lot of other requirements that the solution has to cover. I mean, let us agree, Raspberry Pi solution not always is able to cover safe data storage while using SD cards, as it's hard. And I'm not even talking about backups and replications. But actually is a good starting point for building a comprehensive solution. So this way, I introduced myself to find a way to handle the incoming data and like containing the temperature readouts. So while analyzing the clients and customers' requirements, it became more obvious that the industrial IoT patterns do not actually differ from, let's say, casual IoT patterns that you might always use in your homes. Let's say you got a smart IoT device like a smart plug, and after connect it into internet by pressing the quick connect button on the Wi-Fi router and on the smart device, we are able to see the data that the device produces, like power consumption, and we always are able to act on it, for example, to put it on or off. Well, in this case, the smart plug is data assets. And how does it look in industry? What generates the events? What actually is the nature of data assets? To be fair, it's quite similar to come up with an analogy about heating our buildings. Let's say we are sitting in our buildings and we want to control the temperature. Either if it's on a whole building level, it is on a room level, or even the flat level. The same goes to IoT. In industrial IoT, to maintain production, whether it is in a simple machine, a production, or whole factory set, the component is always the machine itself. But it does not generate events by itself alone. So like the heater to tell us about the temperature, it uses a thermometer. The machine uses various sensors to check the machine current production status and a control cabinet to control the production process, of course. For example, the sensors produce information like temperature, pressure, velocity, vibration, etc., while measuring various factors of the machine work. The same goes to the control cabinet, since to control various machine actuators, it uses several components to calculate and trigger various actions based on the incoming sensor readouts. So for example, to trigger various information, we also might calculate factors like the cycle time of a batch, the production output to see if the product is okay or some of them have to be scrapped, the power consumption, since we are working already with smart power supplies, and other information about the status, the errors, and the warnings. So this already is a lot, and you can agree with me that that might be overwhelming for a lot of people who might be starting with that. But going back to analyzing the customer needs, it came quite obvious that there are several problem groups that have to be covered using IoT. So I identified mainly 3 problem groups that dictate which sensors have to be used to fulfill those requirements for the solution and the way the events are produced. So like in condition monitoring and predictive maintenance, those are slogans that are commonly used in industrial IoT, but behind that stands the information that all we have to do, and the main reason we have to do it, is to monitor the crucial parts of the machine, just to help the maintenance team get the information about some abnormal behavior, or maybe to predict it with some lightweight models. But to control the process and the products on the machine, we might also support this way the quality assurance team with traceability and access control, where the events might be triggered by some control solutions like RFID, radio frequency identifier solutions, like those you use in your access cards or even telephones or smartphones. And also the most common, and you can agree, gaining more and more hype around several sectors in the industrial IoT, is the process analysis for the supervisor team to optimize the production rate. And yeah, this approach actually helps to identify more closely the problem and group the devices into smaller sections that might solve the several problems we defined before. And it would be, everything would be actually great if all those information would come in a common way, in a specified format that would be easy to actually reproduce and analyze. But it is fairly rare if it's going to be in the industrial sector. Well, the challenge actually is to access more, or at least few, of the protocols. And the protocol usage actually more often is is crucial to the whole solution about various factors. For example, from the vendors we use, we might get other communication protocols that are more often used for their solution. But again, if we are lucky and the customer has a setup OPC server, so actually it is, long story short, a local setup database instance, which with some extra steps accesses the demanded data and allows some IT solutions to get those data. The problem comes with using the need to use of the sensors data, and sometimes the sensors do not allow getting all those data in a common way. And this was a problem I had to face. And luckily, I was introduced to Iolink. And just to say it, I'm not paid by anyone to say that, but it is like car manufacturers would agree to use a common part, like common chassis for all the cars that you can buy on the market. The same appeared at the leading industrial vendors that supported a consortium, which is called also Iolink, to introduce a main protocol for the sensor they use. So the case was just to be able to use a lot of different sensors with a common interface that is actually connected into a so-called master, Iolink master, which concentrates those data. And those data are parsed then further into the assets, like those programmable logical controller or human-machine interfaces, depending on the vendor's needs. But luckily for IT, Iolink is quite aware of our needs, and it dictates that all those Iolink masters have to have an open API service, which actually allows for a lot of possibilities to us, again, for getting those data and controlling those devices. And there are really many vendors that already use Iolink for a lot of their communication protocols. And this is only a small snapshot, and I might be aware that it might be not really capable to read, but let me tell you, to print out every vendor, I had to have about 3 pages only filled with all those vendors. So it is a more common used way to communicate with those devices, and this solves the communication protocol and leaves us just with only few few ways to communicate with those devices. And since we now already know what devices, what data assets in the industrial sector and the way the events are produced, where it is now necessary to perform a certain task on it. And to do this, we have to somehow collect those data. And to collect those data, we need a so-called device collector, collector device that is actually called in the formal taxonometry an edge. And although there are a lot of definitions and there is a formal taxonometry created by the Linux Foundation, this slide only shows the way you might want to explore this topic by searching all those keywords. So for all of you who would like to go back to this slide, I just place this information here to encourage you to just gain more knowledge for that. But in many of the solutions that are available in industrial cases, the edge device is more kind of a box with some computing power based on the application needs, of course. And the box should be able to set up a connection with all those devices, collect those data, process it, maybe run a lightweight analytics model or analytics task, store those data, and display it maybe on a simple web server. This is actually all that all that the edges are mainly used for. But in industrial sector, the edge should be mainly used to gather those data, process it with the lowest latency, parse it further into the place where all those apps are working, or maybe the whole IT magic starts. So that means this solution has to be message oriented. And well, for me, for working with this, I had to get familiar with streaming architecture and build a solution around that. So probably for some of you, this is already a common case, and you already are working with well-scaled streaming architecture. But for some of you who are new to this topic, I would like to make this more obvious. So about streaming architecture, it actually demands from us, from the edge, to connect to those data using via several protocols. And since the used protocols are, of course, the most convenient for the sensor or actually the asset, the way we receive the data might be quite useless for us to fit our services with it. So that's why it would be convenient to transform them right away using the lowest latency data formation possible. And this way we are able to obtain all those data in a quite common format that would be really easy to fit the services with. So for example, it would be a JSON object containing the data readouts and also containing some metadata written in, let's say, UTF-8. And this way, we are able to forward them to the services. But like in many cases, the same message has to be delivered to one then more services. So this way, we might have to introduce a message query service. And this handles actually the connection for us. And many of you might be already familiar with services like Apache Flink, Apache Spark Streaming, or maybe RabbitMQ. But in industrial IoT, for its lightweightness and wire optimization, the most commonly used service, which is now becoming a standard, is the message query telemetry transport, or shortly MQTT service. And this allows to really some convenient task to perform. But after all, now looking at this architecture, we might wonder, like I did wonder, would it be possible to have a control on the way the services would be deployed and the behavior of the services? So this way I was introduced to virtualization, and it really excited me. So yeah, like many of you might be already familiar with virtualization engine and the orchestrators, but to stay with everybody on the same page, the concept of virtualization applies deploying the components in so-called pods within a virtual environment with defined network. So the idea is to define the required infrastructure state and the services within the environment, and letting environment engine overwatch the pod's working state. So for example, for me using the Docker engine, I would like to show you an example. I'm just gonna make it bigger for all those of you who are using smartphones. This way, I'm using the Docker Compose feature, which allows me to deploy services like MQTT brokers, Node-RED for rapid prototyping. This is, after all, quite a good tool to do that, a convenient tool to make simple tasks. And of course, InfluxDB, it's a timestamp database. This way, I defined the way the services should be deployed, the network and the ports that should be used, or even use the restart feature to make the pods restart on failure and all the dependencies. So after running Docker Compose app with detached feature, we might be the engine actually creates all those services into containers and deploys them into a virtual environment. And this way, I am able to check whether all those information work. So for example, while using Node-RED, I'm gonna make it this a little bit bigger. We can even like just simulate the behavior of the MQTT service by simulating pushing or generating a value that could be actually generated from a different service into a service that runs a MQTT publisher that publishes this value generated on a topic, for example, this test -hi. And there's another service that subscribes it and logs it into the logger. So for example, if we just generate this value, trigger it, yep, here we got those data that this is highlighted, that came back into the from the subscribe node. So this is quite convenient to use. This is a quite convenient way to use the virtualization engine. But another quite neat function is to use the virtualization and attach it into a CI/CD pipeline. For example, to deploy newer versions of our pods or introduce ourselves into an ML pipeline that would make it possible to deploy machine learning model inferences into our edge analytics pod, for example. The service might be, of course, the CI/CD service might be set up locally on-prem, on an on-prem instance or on a cloud service. And you surely might think, why don't we just clusterize all those edges or use a huge harvester for NVIDIA Titan graphic cards just to train our model locally? Well, to answer this, it might be good to consider the main purpose of the edge. So the main purpose of the edge is to ensure even flow on the productions. And this way we cannot afford increasing the latency of the messages arrival inside this edge. Yeah, clusterizing these edges is okay if the edges are connected within a high bandwidth private network and are relatively close together. But this should be only mainly used for data replication purposes. We cannot afford to increase the latency through ML model training. So it might be convenient to process and train those data outside on a peaceful server. And yeah, the other thing is about the event durability. So while working with IoT devices, it was shocking to me what the main purpose of connection loss occurs around the solution. So you might truly think it's because some crashes or collisions where the edges are destroyed. But the thing is, more often the connection loss occurs because of, for example, maintenance team or production workers who might want to use the connection line that uses the edge. They might think this is not so relevant for the process. And we have somehow to get across that. So in this case, I had somehow make the event message controllable and start inside the flow, somewhere inside the flow, in case of connection loss. So I had to actually introduce the persistent volume inside the to work with the pods, and the amount of persistent volumes shown here is actually used for the worst scenario. For example, for in case of failure for all the other nodes, but after all, a well-configured MQTT broker would do the job using its message retain functionality. So this way, the message becomes more safe from the internet loss and pod failure. But to be safe from edge failure or some kind of distraction causes, there are two ways actually we can avoid that on the industrial level. Either to use two or more clusterized edges with load balancers, or a data asset that actually has its own message query, but that's not really common. And at this point, it is also worth to mention about those orchestrators and visualization engine distribution. So while working in industrial IoT, we might came across a problem to get a hardware device where our edge solution should be work. It faces a lot of problems, for example, the cost and availability. And to make the edges being more affordable, we have to make them smaller and not to use much more capacity inside them. So we have to have in mind that the industrial standard edge hardware does not supply us infinite RAM, random access memory, and storage. But we can afford we cannot also have heavy pods or fully scaled environments. But fortunately, there is also a matching solution. For example, the most common now edge gateways that produced by Siemens, and while having only 2 GB RAM, we can use the Docker virtualization engine with demands only half of a gigabyte of RAM. And if we feel more adventurous and would like to use Kubernetes distribution like that from Canonical, the microcase, which requires more random access memory, we might use the HPE, like we mentioned before, that allows us to run something more scalable. So like that, we went a long way to introduce simply a case to collect those data. And so now what? For me, I knew where events come from, and I also knew how to implement an efficient edge device to keep our demanded services working and avoiding data loss. But what about the app? Where is there a recipe to do that as well? Well, on one of the AWS's IoT conferences, there was a sentence that that I really enjoyed. They said, whether IoT is really technology focused, it is case oriented. So we have to work with a case to simply gather more and more patterns and more blueprints for the app that should be working behind of that. But there's no certain recipe. So let me just share you some information, or let me just share you my experience of working with some cases that I had a chance to do it. So let me start with a small one. The idea was to provide a virtual warehouse app to see the autonomous robot position and current task status. The app should be remotely available, which means it can be deployed on a web service. And what do we get from the data asset, which for this case is the AGV robot, the autonomous robot that actually drives through the factory? Well, it looks like the robot is already IoT ready. So it pushes the necessary data using MQTT service with a publisher client, and it also buffers it into internal queue. So that solves our problem of data durability. So in theory, we should be just able to connect everything into our service, for example, using the AWS IoT Core message MQTT service support. Yeah, it is possible, but the publisher should support MQTT connection, safe MQTT connection, of course, and it also demands manual certificate renewal, which makes the maintenance problematic. And after all, setting the simplest streaming infrastructure and configuring the message forwarding rules for IoT Core, we can feed our application with demanded data. But if you would like to consider the scalability of this solution and, for example, add a local administrator panel for the AGV robot, well, using an edge comes more handy. So this way, with fairly small amount of additional work, we are able to provide a reliable app with local maintenance support. And also it also offers more automated certificate removal while clusterizing all those edges and using a master node. But yeah, we might also add another pod, which allows us to use some kind of administrator panel. Yep, this is fairly it. And it also allows us to scale those solutions. So, for example, if we would like to add data assets along with the formerly used app, we would like just to make it connect to the MQTT broker. And let us see a simple case for now. We would like to add an Iolink master into the edge and gather informations from the RFID head, which reads the tags and shows us the service working with shows us the service working with the light, just to change the status of the light. And yeah, whether it is quite problematic, and it does not look pretty if we just try to connect it for a prototype, and here we can see the master itself with the light, with the smart light connected to the master and the RFID head. All that is connected to powered by the power supply and connected to my computer, just to show you how it works. And let me just show you by changing my camera to show the case. So after deploying our solution, let me just show you the Docker. I had to add to the solution an AWS MQTT connector, which actually only what it does, it pushes the information further, and the master connector, since the master only offers an REST API to connect all those data. This way, we are able also to store those data and be safe from data loss, since the master does not buffer it on itself. So now you can see, while using AWS IoT core, testing it, we can see that the master already pushes some data to our IoT service, which is deployed on the Europe West availability zone. And while ingesting those data into for example, a serverless application, it allows us to, for example, to change the behavior while sending information back to the master using the same communication protocol. So for example, if I just attach my card with my face on it, the system knows, yeah, I can allow you the entrance and the light is green. Yep, that's my card. But if I use another card that is not familiar in the system, yep, it blinks red. So for example, this might indicate that I have no access to this particular machine. And although this is all done only for a simple case for one master, we might scale it up while deploying other pods with environment variables that allow to connect them into another masters inside the network. We might produce a fully scaled up solution. And talking about scaled solution, there's no way that everything might be that easy, and we might have to deal with a big one. So let's consider the huge one case. There are multiple production lines or maybe even factories that we might have to deal with it. The data does not arrive in the same way, and sometimes to cover the functionalities, you might need to add additional assets. So this does not sound really attractive in any way. And if we consider a single line, just to somehow collect those data, we have to use either multiple edge devices, or if we are lucky, there's also a OPC server setup. And next, we have to push those data to a local server, which has to fulfill some requirements to have a maintained working app on it. And this is a lot of work. This is really a huge project. Yep, with a huge project comes huge salary, of course, but there is a lot of things we have to maintain. But fortunately, like I said previously, we are not alone with this problem. There are a lot of vendors we might would like to come in partnership with. The same did I while working at one of my previous projects, where I had a chance to work with vendors like Siemens, who actually offers a well-maintained self-managed on-premise architecture, which allows to access the data from various assets because they've got already prepared communication protocols and manage the edges from a remote server, which is of course also managed on-prem. The same goes to Phoenix Contact. That's the other that's actually the other provider I had a chance to work with, which allows also quite efficient cloud connection to scale the system up, and also provides a custom app development management onto their own PLC Next devices. So this way, we might sum that everything up, that being familiar with the current industrial IoT infrastructure and data assets, we might be able to set up a reliable data collector by recognizing the customer demands and the use cases they want. So for me, working and exploring the topic of industrial IoT made me able to face all those challenges and build something quite amazing to my own company and to our customers. So like in IoT, I don't want to leave you only with that. And I would like to inform you that you do not have to reinvent the wheel again. And I would like encourage you to find me on LinkedIn and maybe discuss some IoT, industrial IoT related topics and share some thoughts or experience. So feel free to contact me, and thank you very much for attending to my webinar. So MC, back to you.